Hello, this is section 4.1 for Calc Survey, and today we'll be talking about local max and local min. In chapter 3, we started doing derivatives, and now we're going to actually use derivatives throughout this chapter, and you'll see how useful they are. So, beginning with local max and min. In the last chapter, we talked about the slope of the tangent line, that's the derivative, and where that slope of the tangent line is 0, as you can see here, important things happen. So suppose P is a point in the domain of F. F has a local minimum at P if F of P is less than or equal to the values of F for some points near P. So that's why we say local. It can also be called relative max or min, but basically it's the highest point within that local region. Same thing here, lowest point in that local region, and then here's another local max. And then the vice versa for the local max. Now, critical points are where your derivative is going to equal 0 or where the derivative is undefined. So that's why up here you can see where we had local max and mins is where the slope happened to be 0, the slope of the tangent line. Okay, and then over here, now you have to be careful though, when the slope is 0, and here's another graph over here. So you can tell at -2, you've got what's called an inflection point where the slope is 0, but that's not one of your local max or mins. So just because the derivative equals 0 does not guarantee that it's going to be a local max or a local min. So we're going to be testing those later in these notes today. Okay. Now, it also says the derivative is undefined. So over here, you've got your absolute value graph. We call this a sharp turn. It's not a mathematical term, but we're describing what's happening. So it's a nice sharp turn. And you can see that this point is actually a local max. That point is higher than all the other points around it. Okay, but the slope of the tangent line, remember we talked about this in class, the slope coming in from the left is not the same as the slope coming in from the right. If you were standing at that point, you wouldn't be able to tell me if you are going forward or moving backwards. Are you increasing or decreasing? So it's not differentiable right there. The slope, the derivative does not exist, but that is a local max. So we'll have to take into consideration when the derivative equals 0 and when the derivative is undefined for these situations. And this is called a cusp. If you graph y equals x to the 2/3, that's where, and that's an example of this type of graph. And then here we got to watch out for when the slope of the tangent line is vertical. And you can tell again, that's not actually a local max or min. So we'll have to be very cautious when we're setting the derivative equal to 0. The numbers that we get, our potential critical points, aren't always necessarily going to be guaranteed to be local max or mins. Okay. And then watch out, sometimes it'll ask for the critical value, and I'm going to want the full point. I'm going to want the actual y value. All right, now max and min of a continuous function must occur at a critical point or an endpoint. So we'll have to be careful. If they set boundaries, then we'll have to make sure we check our endpoints. All right, so here's just an example of labeling. So graph a function with 1 local min, 2 local max, 1 critical point. That's neither a local min or a local max. So a critical point, when you see that term, you need to think when the derivative equals 0. You could make it undefined. You could make a sharp turn or a cusp, but generally critical point, your brain should immediately think, okay, derivative equals 0. But here's just an example that has all those requirements. And then describe the following graphs, be sure. So what I've done is I've just labeled A and C, those would be local max. B and D would be local mins. There you go. Okay, and all 4 of those, notice the slope of the tangent line. If you were to zoom in, it will go flat. All the slopes are 0, right? Okay, so how do you test? When you get a critical point, how are you supposed to test if it's a local max or a local min? So first and foremost, you have to get your critical numbers. You have to find the derivative and set it equal to 0. Those are your critical points. All of these local max and mins are only going to occur at critical points. All right. So let me zoom back down here. Okay, so once you've established your critical points, you're going to want to know when your function changes from decreasing to increasing. Well, you know how to do that. If you look at your derivative, when it goes from negative to positive, meaning the slopes of the tangent lines are negative, and switch to slopes of the tangent lines being positive, you must have a local min. And then vice versa. If the derivative goes from positive to negative, your slopes go from positive to negative, you must have a local max. Okay, so that leads us right into our first derivative test. All right, so use the first derivative test to identify all local max and min for the following functions. All right, so process works the same each time. First thing you do is find the derivative so you can set it equal to 0. You're getting the critical points. So that's what I did. Use the product rule, first times derivative of the second plus second times derivative of the first. And then if you set this equal to 0 now, it's kind of hard to see what the answer is going to be. So what I did is I factored out what we had in common with these two terms. So it looks like I pulled out an x and an x plus 5 squared. See how they both have that binomial? So then after I factor those out of those two terms, I'm left with a 3x in that first term and a 2 times x plus 5 in the second term. Then I just combine like terms here. But now it's nice and factored, ready to set equal to 0. You're good to go. So from this, you get x is 0, -5, and -2. Those are your critical points. That's where something interesting is happening on the graph. All right. So now we create our first derivative number line. This is the first derivative test right here. After you've got your critical numbers, put them on the number line. And this is a derivative number line. We're going to test our intervals in the derivative. If you plug these interval numbers into the function, it's just going to spit out a value that doesn't give you any information. But if you plug the numbers into the derivative and you get a positive number, then that means that the function's increasing. If your slopes are positive, your function is increasing. Then if you plug -3, so notice I'm picking a number between the critical numbers, and I'm going to plug that into the derivative here. And I get another positive. Oh, so that's interesting. At -5, my function went from increasing to increasing. I don't have a relative max or min. Now at -2, when I plugged the number into the -1 into the derivative and got a negative, oh, at -2, I go from positive to negative, meaning my function goes from increasing to decreasing. So I have a local max. Cool. And then at 0, you can see when I plug the number 1 in to the derivative, I got a positive. So I go from negative to positive. And guys, literally get your finger out and draw in the air. Negative to positive means I go from decreasing to increasing. I have a local min. So that's what I did over here. So at -5, nothing. We're not getting anything out of that because I didn't change from increasing to decreasing or vice versa. But at -2, I have a local max, which I did over here. And then at 0, I have a local min. Now, where it gets a little confusing is where do you plug what numbers into what? So once you've gotten your critical numbers, create your first derivative number line here. The intervals go into the first derivative. That's what's telling us what's going on. When you go to actually write your answer, though, your ordered pair is the point on the function. So you're going to plug -2 back into your original function to give me the ordered pair. But that can get a little bit confusing on where you're plugging what into what. So you have to make sure you understand why you're doing it. Okay, now I did the same thing over here. Now I found the derivative. And then, guys, if ever this happens, you have a fraction, you need to get a single fraction to set equal to 0. That's very important. So if ever there's a variable in the denominator, you make sure you get a single fraction, set that equal to 0. Now, you're going to set both the numerator equal to 0 and the denominator equal to 0. We might not include everything. We might throw some things out. Now, from the numerator, you got plus or minus 1, and from the denominator, you get 0. But you'll quickly realize you can only use critical numbers that are in the function. And the function needs to be defined. So if you look up here, see the natural log of x, x can only be greater than 0. So that means we can already throw out the -1 and the 0. So I showed you that here. We throw those out. So really we're only testing numbers to the left and right of 1. And remember, we test these numbers in the first derivative right here. So if you plug in 0.5 you're going to get a negative number. If you plug in 2, you're going to get a positive number, meaning my function goes from decreasing to increasing at 1. So we have a local min, right? Now, once you've established you have a local min, then you plug 1 back into your original function to give me the ordered pair. Now, you need to practice this a couple times, all right? So it is absolutely essential you do your homework with these problems. Okay, now there's another test that does not always work, but it's nice and convenient when it does. So it's called the second derivative test. And it's using concavity to tell you if you have a local max or a local min. So you actually started off, I'm going to move me up here. You started off exactly the same way. You have to find your critical numbers. All right, so notice with this, I did the derivative, factored it so I could easily use that zero product property, and got 0 and plus or minus 1. Those are my critical numbers. All right. Now, instead of making a first derivative number line like I did with the first derivative test, what I'm going to do is I'm going to plug these critical numbers into the second derivative. So notice I took the first derivative and I found the second derivative. And then I plugged these critical numbers into the second derivative over here. Now, what happens is when you plug 0 in to your second derivative, you actually get 0. This is the downside of the second derivative test. If you ever get 0, it's inconclusive, meaning you got to go back and use the first derivative test. The first derivative test always works. The second derivative test, here's where you're seeing the flaw. So if it's inconclusive, you got to go use the first derivative test. So that's what I did over here. I made the first derivative number line, put my critical numbers on there, and I quickly tested 0 and realized, oh, remember we test these intervals in the first derivative, got a negative, nothing's going on there. Okay. So then I come back. Now when you test the other critical numbers in the second derivative though, at -1 you get a negative. Well, if the second derivative is negative, that means your function is concave down. And if your function's concave down, this must be a relative max. And then at 1, if you test that in the second derivative, you get a positive number, meaning the function is concave up, so you have a relative min. And that's using the first and second derivative test. Now, the most convenient time to use the first and second derivative test is when you have polynomial functions. All right, but yeah. So please, please, please make sure you do your homework and bring any questions you have to class. Okay, thanks.